Professor Chris Wise is not your average scientist. He doesn't spend any time in a lab looking down microscopes. Instead, he designs and builds some of the most exciting, cutting-edge structures in the world. To do that, he has to push technology to the very limit. It's a case of mind over matter.
When I was very, very young, I had an idea for a very, very fast bike. In fact, probably the fastest vehicle on the planet. It was a way of linking lots and lots of cogwheels together, one after the other. A big cogwheel to a smaller cogwheel to a big cogwheel to a smaller one. About 20 in sequence. And if you joined them all together and only had a wheel at the very back, by pedaling at the front, you'd end up with an amazingly fast bike. I asked my dad if he would buy me the cogwheels. He said he would like to, but he just thought it was a bit risky and it might not actually work.
Would it have worked?
No, it wouldn't have worked. There's too much resistance to each of the turning things. That's what I found out later. But to an 8-year-old, it seemed like a really good idea.
Chris has always loved building things, but he didn't always know he wanted to be an engineer.
I went and did civil engineering at university. Almost changed to do medicine. Almost changed to do architecture, but stuck it out to get a degree, still not really realising what engineers did. And it took me 2 or 3 years after that before I realised that it wasn't just mathematics. You could actually design things. You know, you could make things, and you could do bridges, and you could do towers, and you could do stuff like stadiums, and which was amazing, and it was a revelation.
Chris isn't the first engineer to push the boundaries of what it's possible to build. 800 years ago, one of the most extraordinary buildings in Britain was constructed on Salisbury Plain, and Chris regularly comes to visit.
This is my favourite building. It's Salisbury Cathedral. It was built 800 years ago, and if you imagine what it must have been like for the people who built it, and imagine coming around the corner and seeing something like this just rearing up in front of you, it would just be absolutely amazing. I think of it a bit like imagining a spaceship landing in the middle of the countryside. You know, it would just be mind-blowing, and I really would love to do something as far ahead of its time as this building was when it was first designed. Well, when I first came here 20 years ago, I wanted to study it as a piece of engineering and to use it as an example of how to use materials very well. And that's what I thought was the most important thing. But every time I come here, I find it just inspirational. I mean, I'm standing in sunlight, and they've designed the building just to allow the light to pour in through the window. You get an uplifting experience, and that's what great architecture is about, what great design is about, what great technology is about. And if you think about this building being designed and made 800 years ago, when most people were living in little tiny wooden huts, and to come to a place like this with the light pouring in, I mean, no wonder they were religious, no wonder they believed in God and the heavens, because they tried to make it on Earth using their technology. What they wanted to do was end up with a fantastically transparent religious experience inside these cathedrals. So they invented a system called flying buttresses, which are these big diagonal stone struts here. And what they do is they collect all the forces from the roof and the ceiling, and they take them past the wall, right across this lower roof, into these big columns and down to the ground. They collect all the forces. And to make sure the forces go to ground, they loaded up the columns with these little spiky pinnacles, and they force the loads downwards.
But Chris has been influenced by more than just the flying buttresses. He's also learned from some of the building's less visible qualities.
In the middle of the winter time, if you go into a cathedral, it's a little bit warmer than it is outside, because the stones keep some of the warmth from the sun. And in the summer, when it's hot outside, it's actually cool inside. It's much cooler in here than it is outside today, for example. And I try to use some of that thinking in the buildings that we're designing nowadays.
At Duxford Air Museum near Cambridge, Chris worked with the architect Sir Norman Foster to create an award-winning building to house a collection of American warplanes. The huge vaulted roof is the largest in Europe and had to be strong enough to carry the weight of some very large aircraft. The design appears very simple, but it requires great skill and ingenuity to achieve.
This is a lot like Salisbury Cathedral, although it may not look like it. And it's got warplanes instead of bishops inside it. But it works in the same way, and it uses this big concrete shell, which is the roof structure, to control the environment inside. At night time, just as at Salisbury Cathedral, it stores all the cool energy. So during a hot day, it keeps the temperature down inside and makes you nice and comfortable. Also, like the cathedrals, we've cut through the edge of the building to bring the daylight in. And these little steel arms, a bit like the flying buttresses in the cathedrals. And what they do is they take the big forces, there's about 100 tons in each of those arms, take the big forces across the space where the light comes in and takes it into the ground, which is over there. And this building is buried in the ground as well. The bit we're standing just behind here is earth, and that helps to control the temperature as well. So we've learnt a lot from the way that the ancients built their cathedrals and some of their other structures.
To construct a building as advanced as this one, Chris needs to know about materials and their strengths, as well as the mathematics of how they work. But which comes first, the design or the maths?
The maths is vital, and without it you can't make sure that anything will work. But if you have the wrong design, it doesn't matter how good the mathematics is, you just end up building something that's horrible. I mean, we could have made this a rectangular shed if we wanted to, or a triangular shed for that matter, which actually might have been quite good. But we decided to make it this beautiful curve. And that's the thing that people will respond to, you know, emotionally and intuitively. We felt that was the right form. The whole building's like an eggshell, really. What you can't see is this roof is made out of 2 layers that are only 4 inches thick. They span 90 metres, so it's almost the same distance that Linford Christie would run in the 100 metres. It's a very long way. And just like an eggshell, you can go a very long distance with a very thin layer of something. It's pretty hard to make an egg unless you're a chicken. So we had to find a way of making an egg, but much more simply. It's really difficult to make an egg because if you look at them very, very carefully, they just curve by a different amount all the way across. So if you can imagine trying to make an egg, you'd have to make that piece curving very tightly and then this piece curving very gently, which would mean, especially if you want to make it out of concrete, you'd have to have a separate special mould for each little section. So you'd have hundreds and hundreds of different moulds. And we actually made this entire roof just using 5 moulds, so obviously it wasn't an egg. Well, we couldn't make it like an egg, so we had a bit of a think, and in the end we decided we'd make it like one of these. And there's a good reason for that. You can imagine every single little piece of this donut as you go round in a big circle. That piece of donut is the same as that piece, which is the same as that piece. And so all we did simply was just to, cut it out of this donut. There's the front. There's the back, and there's Duxford.
Chris gets ideas for his buildings from all sorts of places. For his latest one, he remembered a favourite landscape.
5 years ago, I was down in Cornwall in the middle of the winter, and we went for a walk one afternoon. And it was January, it was really, really cold and very sunny. And I remember walking along the middle of the county towards Land's End. And the light was just amazing, and you could see everything really, really beautifully clear. And I suddenly realised what was happening was the sun was bouncing back off the water and reflecting up into the sky and sort of etching everything out of solid air. And in a way, what we were trying to do when we designed this bridge was to get some of that feeling of just walking through the air and having the light bouncing back, a sort of blade of light, as Norman Foster called it.
Chris had to turn to a new inspiration to build this blade of light.
The Millennium Bridge is like 2 giant guitar strings, and you just walk down them. Of course, like any guitar, it can vibrate. And when we designed it, we checked that really carefully to make sure it didn't vibrate too much. The way that it carries the load is that the tighter you tighten these strings, the less they sag in the middle. And so the Millennium Bridge is tightened between the 2 sides of the river with 2,000 tons pulling against each bank, which is enough to carry the weight of 5,000 people.
The first sketches for the Millennium Bridge were done with a group of colleagues in a bar in London. The basic shape of the bridge has remained the same ever since. But would it work?
The Millennium Bridge across the Thames was open to the public for the first time today and then promptly closed. Police stopped people going across because of concerns about how much the structure was moving in the wind. The design of the slender bridge means it is supposed to sway, but the fear was that with so many people crossing, some of them might be injured. Our reporter Gillian Hargreaves is on the bank of the Thames. Beside the bridge, is it open, Gillian?
Can you feel it moving from there? Yeah. Can you? Just a little bit.
Chris has brought his son Tom to the opening day.
It's not so bad. It's when these great waves of people come past that's what causes it, isn't it?
Why is it wobbling?
Basically because it's strong enough to carry their weight, but sideways it's not quite so strong. And so it's not so much a question of strength. I mean, it won't fall down. It's because it's just vibrating, again, just like a guitar. And you can feel it vibrating about once every second, sideways. And what we really want to do is probably we'll do something just to slow down the vibration eventually. But this is like a sort of full-scale experiment, this bridge. Never been done before. I mean, 10 years ago it would never, ever, ever have been done. And so we've pushed the technology of bridge construction forward a bit. And so it's not surprising that you get the odd little thing which doesn't behave quite as you'd hope. God, it's amazing. I don't know whether it's good or bad. Most people don't mind it, but some people feel a bit uncomfortable, as you can see. I think the Millennium Bridge is a bit like a Formula One racing car in terms of bridge design. It's right at the leading edge of what's possible. And in fact, as we've shown recently, it's just beyond what's possible, and we've got to do a few things to fix it.
To get away from it all, Chris decides to go on a climbing holiday to Wales with his girlfriend Catherine. Unfortunately, the weather's not on his side either. But this isn't any old climb. They've got all the gear. So, why does Chris take climbing so seriously?
Because I got very scared up on a place near Mount Snowdon about 7 or 8 years ago. And we were just out walking. And it was a day a bit like this, except it was in November rather than July. And it was so slippery, I thought I was going to fall down and kill myself, basically. So I swore I would never, ever, ever go up in the mountains again, unless I knew what I was doing. And I went straight down from there. I went to the climbing wall in Mile End in the East End of London, and learned how to climb. It was mind over matter, you know. I was very scared of it, but gradually, as time went by, I became a bit more used to the idea of being a long way up. There are lots of engineers, climbers, lots and lots and lots. I think partly because you need to learn some technique, and then you have to sort of learn how to control it. But at the same time, if you can control it, you can do all sorts of amazing things, and there's some parallel there. It's very mechanical. You use your body as a piece of machinery, which I think is a lot of engineers use their body to sort of try and imagine how a building might work or a bridge might work. They sort of imagine their arm, what happens if I put a big weight on the end of my hand or something. And you can feel all the forces going through your body. And when you're climbing, it's a bit like that. You're hanging off the rock by one hand.
Chris, how's it going up there? It seems very wet.
Most of it's really, really slippery.
Chris, I think this might be a bit dangerous. It's a bit risky.
Yeah, it's not too bad, but it feels a bit unsafe. Maybe we should go down the climbing wall.
I think that'd be a good idea.
Yeah. All we're going to do is get down now.
From the dizzying heights of Snowdonia, it's time to get back to work planning the next building. For Chris, work and play are very closely linked. His hobbies bring a vital extra dimension to his work.
Most engineers are trained to have very, very narrow thinking, you know, to think about nothing but mathematics. And it's important to have some mathematical training and to be logical. But really, you need to be able to understand nature and people and You need to have a broad experience. I mean, the best engineers I know are good rugby players, or they like rock climbing, or they like going to art galleries, or going to the theatre, or they do things which have nothing to do with engineering, but they just have an interest in the world in general. Those are the best ones. The worst ones usually are people who do nothing but mathematics. The best thing is the social side of it, because engineering you don't do it on your own. You do it as part of a huge team. We did the tallest building in Europe about 5 years ago. We got nearly £5 million just to do the design for it, which is a lot of money. But we had a team of about 30 people working on it, and some of them were in Germany, some of them were in London. And we used to fly backwards and forwards between London and Frankfurt, once a week or something. And everybody got really, really, really friendly, because we were all working, we all had the same aim, the same goal. Some people got married, actually, within that team as a result. One person got divorced. But it's very sociable. It's a bit like a sort of grown-up school or grown-up university. So as well as having a reasonable standard of living, you get an amazingly adventurous lifestyle as well. I'll give you the key and then you can open the door, right?
Okay.
Yeah?
Which lock is it? Or will they both lock?
I think it's that one down the bottom there. So.
Okay.
Since opening, the bridge has been closed to the public, and the engineering team has been working on a solution to the famous
It's
wobble.
a bit different to last time, isn't it?
Way different.
And can you feel it wobbling?
Yeah, kind of. Little
No,
bit.
that's not. You're not supposed to say that. All right, start again. Okay, ready? Can you feel it wobbling this time?
Not at all.
No. Let's see if we can get it going, shall we?
Yeah.
I'll tell you what. Ready? Let's jump up and down.
Okay,
Ready?
3, 2, 1. Over then.
No, it's not working, is it?
How are they going to fix the bridge then?
How are they going to fix it? Well, the basic problem is these. You see this joint here?
Yeah.
What's been happening when the bridge moves sideways like this?
Yeah.
The bridge opens and closes each of these joints, and so they're going to put a damper in at each of these joints. Do you know what that is?
No.
I'll show you. It's made out of a little pot like this with some goop in it,
Yeah.
and then a little piston like this. So if you imagine one of these being set in here like this,
Yeah.
right? And then the piston goes inside it. Just try and push that piston backwards and forwards inside there, but don't go into the goop. Just go backwards and forwards. So you can see that moves. If that was opening and closing, that would move really easily, wouldn't it?
Yeah.
Okay. So now try it. Imagine the goop's there. Now push it into the goop and see if you can do it. Give it a good old push. See whether it... Is that easy? Oh, yeah. Now pull it back. Imagine the bridge is going the other way. Oh, yes. And push it the other way. Now it's moving more easily. Oh, yeah. Look at that. So that's much harder, isn't it?
Yeah.
So every time that goop changes its shape, it absorbs energy.
Yeah.
And it actually is it's the changing shape of the goop that absorbs all the energy, and that's the thing that damps down the vibration and stops the bridge from actually moving.
So, will the bridge ever be fixed?
Yeah, it'll be fixed. It's going to take a few months to fix it because we've got to buy all the dampers and put them in, but a few more months and then anyone can walk over here and it won't wobble.